Okay, so good morning to everyone. Can you hear me well? Uh, I cannot hear you, I think, but if you can you write in the chat? Okay. Okay, so can you see my slides too? Yes, okay, so let's get started. Okay, so good morning to everyone. This is the last session of this tutorial on learning to quantify. So before getting started, what I wanted to show you today is a brief overview of Quantify, which is a quantification software that we have developed ourselves. That is, is publicly available, and we want to be reviewing some of its features and how to set up the environment for performing experiments on learning to quantify. But before going into the details, I want to cover this last part regarding model selection. Um, it was one of the things I wanted to cover in the last session, but for reasons of time, I couldn't. So, okay, so what is model selection? Okay, so model selection is the process by which the hyperparameters of a model are chosen. This is important because we know that machine learning methods typically depend heavily on how these hyperparameters are chosen. And this process actually amounts to exploring different configurations of hyperparameters and testing them on a held-out validation set. And because the models need to be evaluated, this process is inherently related to evaluation. And again, because quantification has specific evaluation measures and specific evaluation protocols, this implies that model selection should rely on these specific measures and protocols. And this is important because many of the quantification papers that have been proposed so far, some of them even by ourselves, in which quantification methods that were being used are of type aggregative, so are quantification methods that use the classification, that use the predictions issued by an underlying classifier. Many of these papers have carried out model selection for setting the hyperparameters of the classifier following a classification-oriented protocol. And this should be considered to be wrong because we are doing a different task. Quantification is a task on its own right, so it would make more sense if model selection specific to quantification. Okay, so let's see what people have been doing all this time. So this is how you typically would carry out model selection for classification. And this is something that we should avoid doing in quantification. So the idea is that in classification, you have a training set, which we call L, standing for labeled, which is typically split into a proper training and a validation set. This is typically a partition. We can use some stratified method for this split. But the thing is that this LTR, which is the training split from the dataset L, is what we use for training our methods with different hyperparameters. And this LVA, standing for validation split validation set, is what we use for evaluating our methods when we set these methods with different hyperparameters. So this is what we would typically do in classification. We would take our training set L and we would generate many such splits, probably following 5 or 10 k-fold cross validation strategy. Typically we set k to 5 or to 10, or for this slide, for the sake of simplicity, I am only performing one train ball split. Okay, so the idea here is that we have a set of hyperparameters that we want to test, and these hyperparameters could be simply combinations having to do with the classifiers, hyperparameters. Let's say that we have only 4 different settings, theta 1 to theta 2, theta 3, and theta 4. The idea here is that we simply take the first set of hyperparameters, theta 1, we fit our classifier using LTR as training instances, and we measure the error on the validation set. Once we have tested all the hyperparameters that we want to test, we simply pick the configuration that yields the lowest error. In this case, this amounts to choosing theta 2. So this is our selected model. So we go with M, our classifier M, when hyperparameterized with theta 2. And this is the model we choose. This is the model we confront with the final test. This is what we typically do for classification, but this is incorrect for quantification. And the reason is that because we are interested in class prevalence estimation and not in classification performance. So this means that we should measure the error in terms of quantification error. So what we would do is the following, is to apply a protocol which is specifically designed, devised for quantification. In this slide, I'm using the APP protocol. This is something that Fabrizio has explained in his lecture, standing for the artificial prevalence protocol. Again, this protocol amounts to taking our training set L and splitting this training set into a proper training set, which is LTR, and a validation set, which is again LVAM. And the idea now is to use this validation set to generate many samples, each characterized by different class prevalence. So the idea here is that we are using these pi 1, pi 2, pi 3, and so on and so forth, which are different class prevalences for the positive class. Here I am assuming that we are in front of a binary quantification problem. So we first take, for example, pi 1, in which the number of positives is something like, we could imagine something like 10% or so, and we generate many samples exhibiting this class prevalence. So we have S1, superscript 1, upperscript 1, and so on and so forth. We generate M of them of length Q. So we have Q instances of documents or whatever in our set. We do the same for P2, we do the same for pi 3, for pi 4, and so on and so forth. So we end up generating many samples in which we can test the entire spectrum of prevalence values. Once we have them generated, we simply explore all the combinations of hyperparameters we want to test, and we do exactly the same thing. We train our quantifier, in this case M stands for quantification model. So we train our model on each of these combinations of hyperparameters, and we measure the error across all the samples that we have generated using the APP protocol. Again, we take the model that yields the lowest error, the lowest quantification error, so we can imagine that these errors corresponds, for example, to absolute error or to relative absolute error, or for the fullback library divergence. It doesn't really matter for this example, but this should be a quantification error. Okay, so in this case, in this example, we would end up choosing theta 1 as the best set of hyperparameters. So the model we would select is M when parameterized with theta 1. This is the model that we use for evaluating the model that we use for confronting the test. And you know, in test we do exactly the same. So we use our unlabeled data. In this case, are labeled because we are in an experimental setting. In real cases, we don't know the labels. But for experimental purposes, we have a data set which is actually labeled. And so we can use these labels to generate, again, using APP, many different samples characterized by different prevalence values. We confront our model parameterized with theta 1 with all these samples. This is the error we should report as the result of our method, as a representative of the performance of our method. Okay, that's pretty much it about model selection. So before concluding this part of the lecture, let's take a look at Quantify. Okay, so I'm gonna share a different okay. Okay, you should now see Quantify. Is it correct? Am I sharing my screen now? Okay, thank you. Okay, so in this part of the lecture, we are going to be reviewing Quantify, which is an open source software library for quantification. Quantify is something that we have implemented ourselves and represents the first publicly available quantification framework for research and development. It is currently in its 1.7 version and is, constantly growing. So the very first thing we have to do is to install Quantify, and Quantify can be installed using pip. So let's run this. Okay, we have installed Quantify. These are some useful links. So, for example, this is the project. You can take a look on it in GitHub. And it comes with a wiki, in which there are many examples explaining how to deal with data sets in Quantify, or how to, for example, evaluation protocols that are implemented in Quantify with some examples. And Also, for example, you also have explanations of the evaluation metrics, evaluation protocol, how to set up some specific methods like methods relying on SVM curve, and so on and so forth. And it also actually comes also with developer API in which you can take a look at the interfaces which are implemented in Quantify, how to properly use these functions, which are the parameters, which are the restrictions, which are the expected values, etc. But I'm not going to cover this in detail. I want to show a brief overview of Quantify. Okay, so the first thing is to import Quantify. Some of the most important features in Quantify is that Quantify provides implementations of many methods, including basic and advanced methods from the literature. All methods in Quantify implement the same interface so that it is really easy to switch from one method to another when you perform experiments. Quantify also provides some most typical evaluation procedures, including the artificial prevalence protocol that we have seen in the lectures, but also another popular such protocols like the natural prevalence protocols and some experimental protocols we are trying to devise. So it also implements many evaluation measures which are customarily used for the evaluation of quantification systems. And there are many standard data sets which are used in the literature. So for example, there is this Kindle dataset that we used in our previous lecture, and Quantify currently supports something like 50 distinct data sets. And it's pretty easy to simply fetch one or the other and experiment with differently characterized data sets. So some of the data sets have to do with text, some have to do with sentiment, polarity. Others simply come in vector forms or numerical data sets. Some are high dimensional, so there are low dimensional, and so on and so forth. So you can experiment with your methods in data sets which exhibit different characteristics. Okay, so Quantify brings also native support to multi-class quantification. So recall that in our previous lecture, we have only dealt with the binary case. That was for sake of simplicity, but many problems, many quantification problems are actually characterized by more than two classes. So for example, in sentiment quantification, we could have negative, neutral, and positive categories, while in ordinal classification quantification, we may have some very negative, negative, neutral, positive, and very positive categorized, and so on and so forth. So Quantify implements provides native support for multi-class quantification. Quantify also implements procedures for performing model selection. This is what we have just seen. I'm gonna also show you how to perform model selection in Quantify. Quantify also provides visualization tools which are convenient for analyzing the performance of a quantifier in order to gain some insights into which are the regions in which your method performs best or worse. And finally, it is open source. It is in GitHub, and it's pretty well documented, I hope. Okay, so this is all for this introduction. Okay, so let's take a quick look at the framework. So The following example uses the Kindle dataset, and it automatically downloads it the first time, and then automatically generates the DF-IDF based words representations by also dropping infrequent features. Here we are dropping features occurring less than 5 times in the dataset. And the fetch function returns the dataset, which is nothing but a label. It is a pair of label collection objects. It has the training set and it has the test set, because these two splits, these two partitions were, are now considered to be standard. So in this example, we are using the adjusted classify and count. This is how you use ACC in Quantify. It is an instance of, it is included in the package in the module aggregative, which is a submodule of method. And of course, you have to provide a classifier. In this case, we are using logistic regression as implemented in scikit-learn. Okay, so let's simply run this cell. As you can see, the model is downloaded for the first time from Zenodo. This is only carried out the first time. So the second time you invoke fetch, the dataset should be stored in your disk, so it is not downloaded again. Okay, datasets have been downloaded and conflated, and this is the mean absolute error we would obtain by testing our method directly on the testset. Okay, so but as mentioned before, not all the datasets are binary. So let's see how to work with single label datasets. So multi-class datasets. In particular, we here use the HCR dataset, which is one dataset for sentiment analysis consisting of tweets labeled according to 3 classes: so positive, negative, and neutral. Okay, I'm going to download the datasets. So as you can see in this example, everything is transparent to Quantify. So the fact that this dataset has 3 classes imposes no additional requirement for the code. So we are simply running the code just as before. This is taking a while because we have to download the entire tweet dataset, but we can simply, let the computer download while we move on. Okay, so before moving any forward, I would like to make sure that there is no question, you can hear everything well. Although I think I cannot hear, but I'm going to try to figure out why once the session is, when the lecture is over. Okay, so this is taking a while. Let's simply move. Let's simply go ahead. It will eventually end. Okay, so not all the methods are multi-class by default. Some methods have only been defined in literature for the binary case. So in this is one example, is the HDY method. This is standing for the Hellinger distance on the space of posterior probabilities that we have seen in the second lecture. And this method is binary only. There is actually one variant of this method which has been proposed in the literature by Firat, and which he proposes a multi-class extension of this method. This is also implemented in Quantify, but because ACY was originally designed and devised for binary quantification, this version of the method is binary only. And I'm going to use this method as an example of a binary quantification method that one can be converted into a multi-class one by applying this one versus all strategy. This is pretty much the same as in other frameworks like in scikit-learn, and it basically amounts to generating one independent binary quantification problem for each of the classes, then issuing predictions for each of the classes independently, and finally normalizing for the for the entire number of classes so that all of them sum up to 1. Okay, so our first method is about to finish. Let's wait a couple of seconds because we will use the same data set here. Again, this is only carried out the first time. Okay, so the dataset is downloaded. The datasets are completed. Now the method is training. And that's it. So we have trained our method. And this is the new absolute error we obtained for this case. So as you can see, switching from binary to multi-class is transparent. Now let's take a look at HDY in the one versus all strategy. So one versus all actually returns an abstraction of a quantifier which is natively multi-class. Okay, it is now training the different binary instances. Yeah, and that's pretty much it. We have our estimate prevalence. Let's take a look at the result. Oh no, okay, well, I have run the model again. Sorry. Well, let's see how this one versus all variant performs on test. In Quantify it is typically you can usually indicate this n jobs -1 when there is something that could be parallelized in order for Quantify to run them in parallel. Okay, so this method produces an error which is significantly higher than ACC for this dataset is 0.1 in terms of mi. Okay, but in our last hands-on lecture, we discussed the APP protocol, and there exist other evaluation protocols like the natural prevalence protocol, or we could simply try and devise a new protocol, maybe something which better reflects the phenomenon of our specific applicative scenario. So the idea is that protocols are abstracted in Quantify specific classes, which are, is something that generates samples. So in Quantify, these are defined in the protocol module, and most protocols can be configured to generate samples of a given size, because it's kind of uncomfortable to indicate the size, the sample size everywhere. Quantify has some, environmental variables like sample size that we can set once and for all. So for example, we set our environment variable sample size to 100, indicating that every time we apply any protocol, we would be generating samples of size 100. Okay, so this is how we apply the APP protocol in Quantify. So this function evaluate is something that takes any quantification model. In this case, it could be our one versus all strategy, or or ACC, or any other quantification method. We indicate a protocol, an evaluation protocol. In this case, we are using the APP protocol, which is requested to generate many samples out of the test data set. This is the number of repeats, the number of samples we want to generate for each of the prevalence values in a grid. In order to keep this example fast, fast and simple, I will simply generate one. And this is the error metric that should be used for evaluating the model. In this case, we use my, and you can indicate this as a string. And verbose is just to have some outputs while Quantify is performed. Okay, so we have the mean absolute error here. This is the error we should report when assessing the performance of one quantification method using a well-designed evaluation protocol. Okay, so it is sometimes convenient to report and analyze the performance of a quantifier in terms of different evaluation measures. Let me run this style so that our model is ACC, which is much faster. Okay, so in such cases, Quantify can be asked to generate an evaluation report, which is a pandas data frame which keeps track of all the details in the evaluation. So for example, it keeps track of the true prevalence values of the samples. It keeps tracks also of the estimated prevalence values of each of the samples. Also can keep track of different evaluation measures, different errors, which are which are reported for each of the samples. We can simply get the averages, using standard pandas functions like mean. So this is one example of the report we would obtain. In this case, we have generated something like 230 samples. This first column indicates the true prevalence of each sample. This second column shows the estimated prevalence values for our quantifier. This is the mean absolute error, mean relative absolute error, Kullback-Leibler, and normalized Kullback-Leibler divergence. And again, we can obtain the averages just by computing the mean of the report. And this is something, this is the output, this is the accuracy, the error, the errors that we obtain using, in this case, ACC in the dataset HCR for a ternary problem. Okay, if there is not any question. Okay, so let's move to model selection. So, you know, as I have already mentioned in machine learning, the performance of the learning algorithms depends heavily on how we choose how we indicate the hyperparameters of the model. And these hyperparameters, you know, are something which is not part of the learning procedure, is something that cannot be learned during the learning phase because they control some specific aspect of the learning process, and you know, it's something which makes part of the induction bias. It's something that I'm not going to cover in this lecture, but you know, um, the process by which hyperparameters are decided is known as model selection, and generally comes down to testing how well the model fares when setting different combinations of hyperparameters. So typically, this evaluation for model selection is carried out on held-out validation data. In quantification, again, this means testing the quantification accuracy of a model with respect to some specific evaluation protocol. In the meantime, I'm going to run this piece of code. So in this example, we are going to be considering distribution matching, which is a generalization of HDY. And since model selection is computationally costly, we will indicate that this exploration of hyperparameters should be carried out using some parallel workers. So we set this environment variable n jobs to -1, indicating that every time there is any parallel work to do, Quantify can try and get leverage all the CPUs which are available in the machine. And for this example, we use the Kindle dataset again and generate a validation partition out of the label data in a stratified way. So for this example, we keep 70% of the documents as training instances and the rest as validation examples. The exploration is carried out using this grid search Q class, it's standing for grid search for quantification, which you know generates all the combinations of hyperparameters of this grid. So in this grid, we indicate that the hyperparameters we want to explore include the hyperparameter C for logistic regression, and we want to explore this hyperparameter in this space. Okay, so this is actually akin to exploring 0.1, 1, and 10. I'm going to keep this example as fast as possible, but you typically would rather explore a wider range like this one. We will also explore the number of pins that distribution matching uses. Distribution matching is a method that works somehow similarly to HDY, and in which it first creates some bins and computes the histograms of two distributions. And the number of pins, of course, is something that influences, that has an impact on how the distribution, the matching of the distributions are computed. In this case, we simply explore 8 and 16 for this example, but again, you should rather explore a wider range. So these two hyperparameters, know that there is one hyperparameter which is a classifier dependent hyperparameter. So we have to indicate this as a prefix following, the standard of scikit-learn. And this second hyperparameter is quantification dependent. So we do not have to indicate any prefix whatsoever. Okay, so grid search Q actually takes one model. This is the model, in this case, is distribution matching with a logistic regression. It takes a param grid that generates all the combinations. It takes an evaluation protocol, in this case is APP on a hellout validation split. It takes the name of an error to optimize for. In this case, we use my as a quantification oriented loss. We here indicate with refit true that once the exploration is over, we want to retrain on the whole training set. So we want our final model to be trained not only in this on this data set, but also on the validation set. And verbose, is something that we indicate for having some feedback during the exploration. Okay, this is the result. This is what we would get using Quantify. And the exploration has finished. This is the best combination of hyperparameters that the model has, that the grid search model selection procedure has found, yielding an error which is something like 0.03. In terms of this took something like 6 seconds or so. Once this set of hyperparameters has been chosen, then the model has been refit on the entire development set, on the entire training set. And after this, we evaluate our model using the test set. Again, we apply the APP protocol on the test set. Again, we use mean absolute error as our evaluation measure. And this is the result we obtain for this example. Okay, so let's take a look at some plotting functions which are included in Quantify, and that can be also useful for analyzing the performance of different quantifiers. Okay, so first of all, let's try and generate some experimental results. In this code, we are generating predictions for 6 different methods that we have covered in this seminar: CC, ACC, PCC, PACC, EMQ, and HDY. We are going to use the Kindle dataset. And for the sake of brevity, I'm not going to optimize either parameters here. Because this is only for demonstration purposes. So what I'm doing here is to generate experimental data. I'm trying to to test different methods using the APP protocol, keeping track of for example, the method name, keeping track of the true prevalence values for each of the samples, keeping track of the estimated prevalence values for each of the samples and methods, and also keeping track of the original training prevalence. This is important to measure the bias every method exhibits with respect to the training set. These are some parameters of matplotlib. This is not important for us. Okay, so once we have set our experimental data, we can use some plot functions which are available in Quantify to visualize the results. The first one is something we should be familiar with already, because this is something I have covered in the previous lecture. This is something that Fabrizio himself has explained in his lecture. And this is the so-called diagonal plot, is something which represents the estimated prevalence as a function of the true prevalence when we use APP. This is convenient in cases of binary quantification because we can take care only of the positive class, because the negative class is the complement of this. And this is how you would get some insights into how different methods perform for this dataset. And something that jumps to the eye in this case is that, as we have seen in our lectures, CC and PCC are the two methods which are most biased towards the training prevalence, which is this one. Other methods do a much better job, especially those implementing some kind of adjustment, kind of correct pretty much all the error that the unadjusted versions produces. Again, EMQ is one of the top performing methods, and HDY also in this case produces very few errors. You can tell because they are very close to the main diagonal. Okay, so it is sometimes convenient to analyze the distribution of the errors produced by each quantifier, and these distributions are sometimes displayed in terms of box plots, which is a statistical tool which display in graphical form the quantiles, the mean, the average, and also some outliers of the distribution in compact form. So in this case, we can see that for example, classify and count is biased in the sense that the mean and the median and actually most of the distribution is above 0. We would say that the method is unbiased when this distribution is centered at 0. In this case, there is no perfectly unbiased method, because all methods, even including EMQ, presents most of the distribution above 0, meaning that there is some bias towards the training prevalence. But in this case, this was expected because even though the method is trying to correct for the training bias, the training data has so many positives. In this case, it has something like 91% of positives that this is very difficult. So we should be happy with this kind of performance in which EMQ almost always reduces the bias of this classifier pretty well. Okay, but this shows the distribution of biases as one single distribution, but it would sometimes be useful to analyze the error distribution by regions of prevalence. So in this case, we plot together all the results that belong to the, for example, 0 to 0.2 interval of prevalence, or from 0.2 to 0.4, and so on and so forth. And we generate box plots for each of the regions. So something that again um, seems interesting here is that methods like EMQ and HDY are not particularly affected by the region in which they operate. For example, you pay attention to EMQ, the distribution is not differently distributed in terms of the range of prevalence. While this is not true for other methods like CC. So for example, for CC exhibits a dramatic bias in the low prevalence region. This bias is reduced for the second region, reduced for the third region, so on and so forth. Okay, so these plots are convenient in binary problems mostly because bias is something that we could compute for binary problems, and especially this kind of plot is is rather inconvenient if you work with, I don't know, something like 10 classes, because you would need to generate 10 different protocols, one for each class. And it's sometimes difficult to analyze what's happening there as a combination of 10 plots. So something that we can do instead is to, generate a different plot, which is called the error by drift plot, which is this one, in which we represent the error that we want to measure. In this case, we are measuring the absolute error as a function of the distribution shift between the training set and the test samples. So in this case, first of all, notice that you can generate this plot for any dataset, no matter if the dataset is binary or not, because distribution shift is something that you can measure for arbitrary number of classes. So for example, in this plot, we see that methods like CC and PCC typically exhibit few error in the low drift regions. So in cases in which the samples that are tested are somehow similar to the training sample, to the training set in terms of prevalence, then CC and PCC performs pretty well. Actually, you can see that PCC is the best method in this region here, but this is something that is not true for the regions of the space in which the drift or the shift is higher. So in these regions here, for example, we are observing the performance of our method in regions in which the test sample has a prevalence which is very different from the training prevalence. In these cases, PCC and CC perform very bad. Other methods, again, like EMQ or HDY, perform much, much better, even in these regions. So something which is interesting in this plot is that methods like EMQ and HDY perform very well in the entire spectrum of shift regions. This is something desirable for a quantification method because we want our quantifier to work robustly, especially in cases in which the test prevalence, the test sample exhibits a prevalence which is very different from the prevalence that we have observed during training. Okay, so there are other plots in QAPI. I am not going to enter the details of all of them, but you can learn more from them in the wiki and in the documentation if you are interested. Finally, what I would like to show you is how to use QAPI for performing experiments in your own datasets. So how you could use QAPI for for solving your specific problems, not only dataset which have been implemented in QAPI. So for this example, I assume you have some dataset, of course, because this dataset can be any dataset, it can have any format. What I'm going to assume is that your dataset is the dataset that we have used in the last lecture. Is this dataset.zip, but this this is for this is for this explanation. This is something that you can replace with your data sets. Okay, if you remember this dataset, these datasets are simply plain text files in which we have one value which is a 0 or a 1 for indicating positive sentiment or negative sentiment, and then we have a tab separating the label from the text, and then we have one string which is the review itself. That's all. I mean, this is one simple example of a data set. Of course, you can have any pandas data set or any tabular form data set or any arbitrary format. So the thing is that you have to simply implement a function like this. It's a function which receives a path, which receives the path where your data set is stored, and then you have to implement the logic for for generating the instances and the labels. So in as much as you are able to define a function like this that simply returns a list of instances and a list of labels of the same size, of course, again, in as much as you are able to do so, QAPI will run smoothly. So in this case, we simply provide dataset, which is an internal class from QAPI. We indicate that the dataset has to be loaded using my custom loader, and that these are the two parameters that will be provided to this function. Again, this function reads the files, generates a list of instances, generates a list of labels. QAPI knows how to take care of all of these and generates a data set here called data, which is nothing but a pair of label collections. So you can access them by simply running training and test. And that's pretty much it. This is something that you can now use for internally in QAPI. This is something that now is perfectly integrated in QAPI. Okay, I think this is everything I wanted to cover. Let me stop sharing. And that's all. Again, I will upload everything, all the material, including slides, including code, with some additional comments so that you can check them offline if you want. And I will now be happy to take questions if there is any. If there is any question, please raise your hand. Okay, I see one of you is asking a question, but I cannot hear it. I don't know why.
Hello.
Okay,
Can
I
you hear
can.
me? Yeah,
Yeah.
it's Gizem speaking. Thanks a lot for the wonderful lecture.
Thank you.
I was about to ask, like, the usage of quantification methods that also during the lectures we saw that some use cases are uh, more more applicable for this learning to quantify like area. So I have a problem at hand. Like I have news articles and I have like multi-class classification. I have 4 labels. It's like stance classification, pro, against, neutral, and not relevant, kind of. And I couldn't get sufficient good results in normal like binary classification, the multi-class classification using some like deep neural network. So I just want to see, this is a very large data set. I just want to see the actually the tendency. I'm not interested in an individual prediction, but like overall tendency and overall like estimation. So for this use case, it's applicable, right? These methods.
Yes, it seems pretty much to me that this is the perfect case for quantification, actually.
Okay.
So you mentioned that your dataset is multi-class, but it is single label or not?
Single label.
Okay, single label. Yes, this is something which is pretty straightforward, I think, for quantification. I mean, the problem here is that if you are getting not very good results with your classifier, which classifier are you using?
I was using the BERT model.
Okay, so you mentioned some neural network.
Yeah. No, I'm using neural network. I also checked like logistic regression. I did some like ensembling, model ensemble. Like using different models, like get majority voting and such. But neither did work sufficiently well, unfortunately.
Okay, but this is something that I mean, it's something which would be interesting to test in Quantify because for reasons that we have discussed during this lecture, having a good classifier is not mandatory for quantification. Provided that the amounts of error that it commits is distributed across the classes in an unbiased way. So, in as much as your classifier is able to produce errors which are very evenly distributed across the classes, this is something that quantification machinery knows how to correct for. So I would suggest you using Quantify and exploring using model selection different classifiers. So a classifier becomes one of your hyperparameters.
Okay. Yes.
And you explore them both, maybe using. I would simply recommend you to use EMQ because it's one of the best quantifiers so far. It's very fast and it doesn't require any additional validation set. Having said that, EMQ is a method which strongly depends on the quality of the posterior probabilities. So if you are not sure that your posterior probabilities are well calibrated, then it may be preferable to use something like PACC.
Okay.
In any case, if you want, you can try and set this experiment and you can get in touch with me and we can simply work on it together.
Okay, thanks a lot.
So I can give you some feedback if I see something something strange.
Great. Okay. Okay. Thanks a lot. Thank you.
You're welcome. Any other questions? Oh, let me first stop the recording.